So the next set of topics in the course will focus on atomic classes and operations. And I'm going to explain how Java atomic classes and operations provide concurrent programs with so-called lock-free, thread-safe mechanisms that can be used to read from and write to single variables atomically. And we'll also talk about a couple of human-known uses of atomic operations, although the word human should be taken somewhat with a grain of salt, because these are all from like fantasy or science fiction epochs, but you'll understand where they come from probably. So there's a number of classes that allow atomic actions on objects that are part of the Java Util Concurrent Atomic package. And you can see here there's a whole bunch of stuff that's part of that package. We're going to talk about several of these classes here. One set of classes are so-called atomic variables, and these are used to provide lock-free and thread-safe operations on single variables, not groups of variables, but individual variables. For example, there's a class called atomic long, which we'll talk about in more detail here in just a bit, that supports atomic operations using the compare and swap capability that's provided by the underlying Java virtual machine and the hardware and so on. There's also another class, which we're not going to spend much time on, but I just mentioned because it's interesting, called long adder. And it allows multiple threads to update a common sum efficiently under high contention. So think like some kind of multi-threaded web server that needs to update counts of hits for various pages. And this is a way of being able to do that efficiently. Like I said, we're not going to spend much time on long adder, but I just want you to be aware that that exists. So let's now talk about atomic operations. So the atomic operations that are supported in Java are implemented in hardware with some support from the operating system and the virtual machine or Java execution environment layers. So you can see here that's kind of this part of the stack, right? So hardware's what does a lot of this stuff on modern instruction processors like Intel or PowerPC or ARM. And then the operating system kernel has some features. There's system libraries, and finally those things get exposed up through Java somehow to things that reside on top. The most fundamental operation that's commonly used these days at the hardware level is called compare and swap. And what this does is it compares and swaps atomically by comparing the current contents of a memory location, which is this pointer thingy, and it checks to see if the value at that location equals the expected value. And if it does, then it modifies the contents of that memory location to the given new value and returns the old value. So that's the way things work. So let's take a look at kind of break this down phrase by phrase. So first, this whole thing runs atomically. Now, this is actually most likely implemented in hardware. So I'm just showing you kind of C-like pseudocode to get the point across. But we're going to start out by beginning an atomic section. And when we're all done, we're going to end the atomic section. This, again, is typically done in hardware, but that's the idea. And what it means to be atomic it means that nothing else can be running at that point to interfere with the operations taking place in this so-called critical section. So the first thing we do is we read the location that's pointed to by the lock parameter, which stands for location, and we stash that away in a local field called old value. And one of the things to note about old field is it's local to that thread, so it's not shared by anything else. So we don't have to worry about it being corrupted. We then go ahead and check to see if the old value, which we just read from that location, is equal to the expected value. If it's not, we're done. However, if it is equal, we go ahead and we update the value at that location, the value pointed to by that pointer, to the updated value. So you can see that this compare and swap only works if the old value equals the expected value, in which case it gets atomically updated. And then the last thing that gets done here is the old value is returned. So we can see what the value was before we did the atomic update. Now, once you've got the ability to do compare and swap, you can start to write various kinds of lock-free algorithms on top of that. So here's an example of a lock-free algorithm, even though it's got the name lock. You'll see why it's called lock-free in a second. And what lock does is it efficiently uses compare and swap to implement mutual exclusion, sometimes called a mutex, via a spin lock. And you'll have to know how to do this for your programming assignment B. You will not be using these specific capabilities, but it's along the same lines. So what we do here is we're going to efficiently use compare and swap. And so one of the things about efficiently use compare and swap is we don't actually want to call compare and swap at all if the current value of the location pointed to by the mutex pointer is 0. So if it's currently 0, that means locked, then we're just going to keep spinning in the loop. But if it is not 0, there's a fighting chance we might be able to set it to the right value. And so what we're going to try to do here is we're going to use compare and swap, and we're going to say, if the current value is 0, then atomically set it to 1 and return the old value, which would be 0. So we're going to keep spinning until this condition becomes false. So, basically we negate the results of these things in order to know when to stop. And the thing to note here is the compare and swap is called only once per lock attempt. And this call, compare and swap, is atomic. So if we discover the current value is 0, and we set it to 1 atomically, then compare and swap has succeeded, and then we can go ahead and drop out of this loop. Now, again, this is very subtle code, but it allows us to implement a so-called lock-free mutex, or a lock-free synchronizer. Any questions about that? So this mutex is just pointing to that memory location, and we check to see if the value is 0, and if it is 0 means it's available, then we atomically set it to 1, and we return the old value. Okay. So if compare and swap returns 0, the mutex was atomically locked, so the loop can now exit. So now we can bail out of this thing. Here's the unlock method. So lock is what we do to make sure that we have exclusive access to this critical section we're trying to implement through some other means. I don't show the critical section here. But this is how we release the lock. We have this start atomic block, end atomic block, so that means that runs atomically, and we reset the value to 0. This is actually quite simple. Now, for this to work, an assignment must be volatile. And so you'd have to expect that this would be a volatile variable so that this assignment would be done atomically. Now, of course, in this case, you can see that we used start atomic, end atomic, which are these pseudocode-like mechanisms that this pseudocode-like code uses to ensure that this value is correctly assigned atomically and then propagated to all the other caches that would care about it. There's another way to do atomic operations called test and set. And test and set is actually a little older than compare and swap. It's a little simpler to implement. If you were implementing it in the hardware, there'd be less gates or instructions or whatever. But it's not quite as useful because it doesn't really give you this chance to have arbitrary values for expected and updated. It basically does the following. So it's going to automatically modify the contents of a memory location and return its old value. So once again, we have this atomic region. We are going to set the value of old value to the current value of lock, and then we're going to go ahead and set that value to 1. So we modify the contents, we set it to 1, and then we return the old value. And this will tell us whether or not something has changed its state. So it's not quite as useful as compare and swap, but it's a bit simpler. And this is how you would implement lock-free algorithms using test and set, where you basically keep looping. While test and set returns 1, you haven't been able to change the value, and because it was currently held, but when it returns 0, you went from available to locked. And unlock is basically the same as we saw before. We just set the value back to 0. So test and set isn't used as widely because compare and swap lets you do comparisons between arbitrary values, whereas test and set just checks to see if the old value is 0, and then it sets it to 1, and then we check to see what the results are. So to the point I was just making, compare and swap is a more general solution than test and set. And that's because you get these expected and updated variables. So you can set the value to something other than 0 or 1. And that turns out to be very useful for some of the operations we're going to look at later, like atomic long, atomic integer, atomic Boolean, and so on. So let's talk a little bit about human known uses of atomic operations. So again, this is somewhat fanciful because these aren't really things you would find in reality, but they are found in science fiction or high fantasy. So one human known use of atomic operations, as I've mentioned before, is the Star Trek transporter, which converts a person or an object into an energy beam or energy pattern and then beams them to a destination where they're converted back into matter. This process clearly must occur atomically or a horrible accident will occur. Another human-known use is the apparition or disapparition capability that Harry Potter characters learn if they go to Hogwarts and reach a certain degree of sophistication. And if you focus properly and do the incantation, you'll disappear from your current location and then instantly reappear at the desired location. However, if you don't do things properly, you can splinch, which means that parts of you will be left behind, which would obviously be a problem. So that would be an example of a non-atomic operation. So that's the end of our overview, introduction to Java atomic classes and operations. We'll talk now in more detail about each of those different mechanisms that we discussed in the Java util concurrent atomics package.